simultaneously we decided it's time. You'll notice it's not time. Oh, it's overtime there. It's just time there, and overtime in Fengnan's watch. So we're now drawing towards the last sections of the program. Nothing disastrous has happened yet. There is still time. You have a few hours to have something disastrous happen. So I'm very pleased to have Fengnan speak. He's just been telling me he's moved to Leiden University, where they have data science initiatives. And he's going to talk about preferential attachment, which we've already heard quite a bit about throughout the workshop. So we're going to be doing statistical estimation of the parameters of preferential attachment for network models for preferential attachment. So thank you.
First of all, I would like to thank the organizers to invite me, and also I would like to thank the organizers for the organization of the workshop. It has been a great workshop so far, and I really enjoyed this workshop and all the companies. So I'm going to talk about the joint work with Art van der Waar so far on the statistical estimation of preferential attachment networks. So, as Sophie just mentioned, it has been mentioned, a lot of times already in this workshop. So this is why I'm quite happy I'm working on something that is appreciated by a lot of people. So, it's just a table of contents. Oh yeah, first I would like to point out that I have a joint appointment, not only in the School of Data Science, but also the Shanghai Center for Mathematical Sciences. And both are hiring, actually. So, first of all, I would like to talk about the scale-free networks, which has been kind of some sort of buzzword for the past decade. So, this is the illustration that I captured from one of the papers that appeared in Nature in 2000. So apparently, in this paper, they compared two kinds of networks, simulated networks. One is exponential, the other is so-called scale-free. The exponential, this is the way of the physics saying things. So it is basically Edos-Reni net random network where there is a fixed probability whether each possible edge can occur. And this is the scale-free network. So if we look at both, then we can see that there are more structures in the scale-free network. So you can see that So the red dots here is obvious that the red dots function rather. So first of all, the red dots in both illustrations are the top 5 nodes with highest degrees. So here 5 nodes, here 5 nodes. But it's obvious that you can obviously see that in the scale-free network, the vertex with top degrees play a role. So they really function in this network. However, in here it is just random and chaotic. So they function, and if you cut this away, then all these tiny leaves here will just be lost. So there's scale-free. I mean, the scale-free, the term seems a little bit ambiguous. It simply means that the network looks. It has some sort of similar topography, regardless of at which scale you look at it. So hence scale-free. But this is this physics they're really good at having good names. But essentially it boils down that the scale-freeness basically means the power law degree distribution, which has been mentioned a lot of times in this workshop so far as well. So what is the power law? The power law is basically suppose you have a network, and of course you have a network. Then it's a graph. It's a graph, and you have a graph. Then you have a degree on every node, and then you have a degree distribution by counting the proportion of nodes with certain degree. For example, k. For k, you have a proportion of degree k, and then if it is somehow or in a somewhat sense is proportional to a power of k. As k approaches infinity, then we say that this network possesses the scale-freeness. So, but why are power laws important? Well, it's basically because they are everywhere. Of course, I've read a reference in which they mention that the omnipresence of power law might be just a artifact of the way you sample. But let's forget that for the moment. And pretend it's very important. So also it has a very high it has a very close relationship with the things that happen in sociology, in a lot of disciplines where some sort of accumulative advantage can play a role. So basically, it's like the Matthew effect, where it's in the Bible saying something like, for those who have, more will be given. So basically, you have more, you will be getting more, and this is just the philosophy of this is why the power law can occur. Okay, so for example, the internet, it is known to possess a power law with the exponent of approximately 2, and this is the artistic illustration of internet, which is not that far from this one. So it's yeah, kind of fancy illustration. Also, what I work on is the preferential attachment model, and that came into popularity because of this reference, basically. In 1999, these two physicists, I think both are Hungarian, they proposed a so-called letter, which later was referred Barabasi-Albert model, which is a special case of the model that I'm working on. They proposed this model this is the first time ever that someone in the modern time that came up with some sort of more or less rigorous explanation where a power law can occur. And as you can see, this has been cited so many times. This is 25,000 times. This is have you ever seen? I mean, I don't think there are many references like that. So it's very impressive. So, but why? Simply because people really like power law. They really want to explain power law. And despite that, the Barabasi-Albert model is just a special case of power law with a fixed exponent of 3, still it is so popular. And so let me give a rather precise definition of preferential attachment model. I think a lot of people out here are familiar with it already. So in the beginning, there are different kinds of ways of you start it, but this is the way I started. So at the beginning, there are 2 nodes connecting to each other. Yeah. And then at the time t, you have it's like an algorithm. You have an initialization, then you can start to define things iteratively. So conditional on the graph at time t. Then you look at every node within this network, and you count the degree. And based on this function, this is a preferential attachment function, I call it that, that maps the degree to a real number, positive real number. Then, so for every degree, it maps it to its preference. Well, I call it preference based on its that is a function that depends on the degree only. So then a new vertex comes in, so conditional on the graph at time t, a new vertex comes in, and it needs to make a random it has one fixed edge that needs to be connected to the existing network, and it needs to make a random choice. And the probability that this new vertex picks an existing vertex in the existing vertex, that is in VT, is proportional to the preference of this vertex. So then the new vertex comes in, and then you can start the iterative scheme again. You can do this forever until the end of time, until you have, I don't know, 10 million nodes. So here, for simplicity, we do not allow multiple edges and self loops, but asymptotically speaking, even if allow them, they are more or less equivalent. But for simplicity of our purpose, we do not allow them. So what you get here is basically a tree, simple graph. And also, Barabasi model is a special case where you put this function to be a linear function, a strictly linear function. And it gives a power law of exponent 3. And throughout this talk, we would assume f is sublinear. The reason for the sublinearity is that there is for a lot of random graph models, if you're familiar with the probability theory in these random graph models, there is always some sort of a phase transition going on. So suppose you have a preferential attachment model, and you generate a graph with this scheme. And if f is a function on k, the degree, and if it grows faster than linear with respect to k, then what you end up will be you can prove that with a very high probability that you will end up with a hub, the star. So that's let me give you certain. Basically, it will be something like it basically will be one node, which is a star, and it's connecting to everything else. And and there is some isolated nodes scattered around. But that's basically it. But this is not very interesting. What we are interested in is in more subtle cases. So because if you always end up in a star, that's not very exciting. So we assume that f is sublinear, where so first of all, if f is linear, then power law arises, and if f is sublinear, more subtle things can happen other than linear. So this is what we will focus on. And also, I will point out f is only identifiable. We are doing statistics, right? So it's identifiability issue always arises. So f is only identifiable up to scale by the nature of this model. Because if I may remind you that the probability to attach a certain node is proportional to the preference. But at the end of the day, you need a probability distribution. That means you need to normalize it with the sum. So then that means even if you put a different scale on f, then it will just cancels out at the normalization. So this is just an illustration. So suppose you start with two nodes connecting to each other. Then each one has a preference f1, and then the total weights, total preference is 2f1. Then if a new vertex comes in, it has a half. So it's 2f1 divided by 1f1 divided by 2f1. That's 1/2 probably connecting either of them. Then this vertex choose v1, and then the weights updated. So f2 here, f1, the total weights becomes f1, f2 plus 2f1, and then another vertex choose the v1 again. Then the fifth vertex choose the f2, just random. So it's just an illustration. You can anything can happen. So we are statisticians. We are not physicists or probabilists. So what is our goal here? Our goal here is to estimate f. So estimate f. So this becomes the problem of the. So we are estimating something. So what is the data here? So we observe data, and we need to estimate a parameter. And this f is a non-parametric thing. It is only which we only assume to be monotone. So there is you can pose very little condition on f. So this is really a non-parametric problem. So how do we do this? So first of all, we suppose we observe the entire evolutionary history. So something like this. So something the entire history. It goes on. T can goes on and on and on. Of course, as later as it reveals, we do not need to do this. But still, for the moment, we assume we know everything. And suppose we know everything, then how do we estimate f? And as it turns out that for our purpose of estimating f, so we do not need to know the exact vertex that it connects to. So v1, v2, that doesn't matter. All it matters is that so when a new vertex comes in, it needs to pick one vertex of a certain degree, and only this degree matters. So what you need to do is just write down all the degrees or vertices that in the past that the incoming nodes picks, which we called D here. And this is our data. And so now it boils down to the problem how to estimate f. Also, as I said, so as I mentioned previously, so for the affine f, we have one parameter. So which you can parameterize like this, k plus delta, and delta is the parameter here. So this is one parameter, and you can, as I later will explain, this will result in a power law. And the power exponent depends on delta. And so this is a simple problem, a simpler problem. And essentially it's a univariate problem. So we would come up with a better way of estimating delta. And but how do we do that? So the third question is that suppose we have a parametric sublinear family. So that is parameterized by theta. For example, you can think of this. Actually, this is already a wide enough range of the range is wide enough to cover a lot of possible models in applications. So in this case, how to estimate theta? This is the parameter, and we are going to explain how we can do that. So first of all, I would like to explain the limiting degree distribution of this preferential attachment. So suppose f is sublinear. This is what we will end up. So you can prove that almost surely that for any fixed k, the proportion of the vertices of degree k will converge to something only depend on f. Here f. So it depends on, of course, in a very complicated manner, but still nonetheless only depend on f. So lambda star is also a functional of f as well. So coming to here, maybe you are thinking about the following thing. So we want to estimate f, and we can estimate pk with the empirical degree distribution. So maybe we can sort of invert pk into fk. Well, it doesn't work. So also, yeah, so let me say a few more words about the limiting degree distribution. So if for affine k, if parameterized by delta here, we can write a more explicit form of the limiting degree distribution, which is a special case of this. If you write down everything, so it will become this for affine f with this. And in particular, this means if you write down the asymptotics with respect to k, it will be a polar law with the exponent 3 plus delta with delta here. And also, in particular, if delta is 0, that will be degenerates into Barabasi-Albert model, which is there is an explicit form of limiting degree distribution, which is also why the physics can work it out. So now, as I said, we have to come up with a way of estimating this sublinear f, where we only assume f is monotone increasing. So f is monotone increasing means that the degree increases, so you get a higher preference. So then the higher preference means you have a higher chance of getting attract new connections. So this is a model of rich get richer. So but how do we estimate this f? How do we estimate how much it grows? How much the increase in degree can how much increase in preference can result in from the increasing of degree? And this is the estimate that we came up with. So this is our empirical. What do we call empirical estimator? Then the name has a reason. It has a reason why it's called empirical estimator. I will come to that in the next slide. So, but it is defined like this. So it is the quotient on the top. It is the number of the time for the fixed k. For fixed k here, for any fixed k, the number of times of an incoming vertex. Choose a vertex of degree k to connect to. So in the history, it choose a vertex of certain degree. If it is k, then we write down as a 1. Then we sum it up. And on the bottom, it is a number of vertex of degree k at time n. Seems complicated, right? Well, as it turns out, it's not. So what is the intuition behind E? So this is, you might think, why do you come up with something like such as random as this to say, well, it works? I mean, there is intuition. So the intuition comes from the fact that you think about this graph in the limiting regime, what I call limiting regime. So this basically means because the degree distribution will eventually converge to something fixed. So we just assume that we have a very big graph. And then, in that case, so everything is sort of stabilized, sort of nice. So in this case, what do we do if we want to estimate this f? So as it goes, we do this. So in this limiting regime, the frequency pk of vertex of degree k already is close to the limiting vertex. But that means, so if a new vertex comes in and it needs to pick a vertex of degree k, then the probability of doing that is that the fk is the of the preference put on degree k, and pk n is the number of vertices of degree k. That means the more you have, the more preference you will get, because you will put things equally on different nodes. So then it's just the normalization. Then if you cancel n, and then this is basically something like this. So as I said, this is a constant. This is a constant, and as I said, it is only identifiable up to scales. It's constant, that does not matter. And what we're interested in is in fk. So then if we can get rid of this pk, then we end up with a fk with a factor. So we are good. So we're going to get rid of the pk. How do we do that? We just cancel it. We just divide it by the empirical proportion of pk. So we want to cancel the pk. So we just take the quotient between qk and pk. The pk cancels out, so which is approximately fk with the factor, and this is good. So this is and we would like this to work in the non-limiting region. So that is not so nice, but still So we want to estimate the pk is the probability of a new coming vertex of choosing degree k, and we estimate this by the number of times of the incoming vertex choosing vertex of degree k in the history, divided by the total connections, and also the proportion of the number of nodes of degree k. The problem comes to, does it work? Yes, it works, and the reason for that is that this is actually a crucial lemma. It might not look like a crucial lemma, but it is a crucial lemma, because what this lemma says is that for our particular model of preferential attachment model, that the number so at time n, the number of vertex of degree higher than k, strictly higher than k, is exactly the same as how many times a vertex of degree k got connected in the past. Well, you can read the paper if you want to see the proof, but it's very elementary. So this has a very good has very good implications in our model, because this depends on the history. So this thing depends. You need to count everything in the history. However, this is just look at the final snapshot of the network, and you just count how many vertices of degree k, how many vertices have a degree higher than k, and divided by the number of vertices exactly with a degree k. And this actually is very interesting. So think about this. So Rk is suppose you are a node in this network, and then you are thinking that how much chance do I have to move up, and this is the chance. And this is the chance. How do you estimate the chance? You just divide the number of people higher than you, bigger than k, and divided by the number of people sharing the same rank, which is which actually makes sense, right? And this works. This works, and this works in an almost sure way. So this is consistent in almost sure sense, and so it's a very strong convergence. So I will let me think. Yeah, I will say something about the proof. So the proof is that this is actually how a lot of random graph models go. So typically they come up with some sort of branching process that sort of mimics the random graph model, or sometimes approximation, and then they use the results in the classical branching process that was well studied in the 70s, 80s, and then they say, well, this is then we have our desired result. And in this case here, so we have the result that is this quotient converges to something fixed. And so n bigger than k here is phi here, and nk here is psi here. So then you apply the result. So this will converge to something fixed, and we have the result. So the proof is actually simple. It's I think I don't know. I spent very short time on the proof. But to prepare for the proof, you need 8 pages of notation. So it's yeah. So okay, so it works, and I would like to show you the simulation. So here I have 3 different preferential attachment functions, and I want to estimate them, and I will generate 3 different kinds of number of nodes. So reflecting how far away from you are from the limiting region. And so this is what you have. So this is the box plot. So the red is the ground truth. This is simulation. We know the truth. So as it is obvious that you can see that it works. And for the horizontal level, it is just more nodes. And you can see the more nodes you have, the better the estimate becomes. And this is the slower. So the slower the f grows, that means it's less likely that you put higher preference on degree with higher degrees. That means you have less higher degrees. Then the degree kind of cluster on the nodes with lower degrees. Then you have more observation here. So so when f grows slower with respect to k, then you have a better estimate for k with lower degrees, because you have more observation. Okay. So also I suspect some of you will ask me what is the asymptotic distribution of this empirical distributor, and I can tell you it is the asymptotic normal. Why? Because I don't have a proof, but it's the QQ plot. So but it looks very normal. Come on, it must be normal. But yeah, I need to come up with a more clever idea to prove it's normal. So okay, so as I said, so we people really like to have to estimate the power law, and in our case, this corresponds to the special case where the f is a Fourier function that is parameterized by the parameter delta. And so how do we estimate delta here? So first of all, we know, as I mentioned before, this empirical degree distribution will converge to a power law. And so this is basically pk proportional to k plus k power minus 3 plus delta. So that means if you take log on both sides, that this becomes something like this. Then you would think that maybe you can perform some sort of regression on pk against the log k. Then you estimate the what is it? The slope, which is 3 plus delta, and you minus 3, then you get the delta. Well, but this doesn't work. So because the reason is simple, because this doesn't work. It doesn't even work in simulations, because if you try to fit a line to this some sort of degree plot, then it's very hard to say which line is which one. So how do you know this one is better? How do you know this one better? It's very hard to say. Okay, so but what do we do here? The way we estimate this delta is that we do maximum likelihood. Well, how do we do maximum likelihood? First, we write down the likelihood, then we maximize it. So and this is exactly what we do. And the point is perhaps that it is this. So we can prove that the estimator, maximum likelihood estimator, follows the asymptotic normal law with asymptotic variance. This is actually the inverse of not the inverse, the Fisher information that comes from likelihood. But the point is, it only depends on delta naught. So you can work this out exactly. So you can even give confidence intervals for the delta. So it's very nice. Everything works very beautifully. So okay. So but we like to push this further. So first of all, as I said, the model that I gave was the model with so every node comes in with one fixed edge to connect to. But this is not really normal. There are many smart things you can do, but one of the things that you can do is that you sort of imagine that when every node comes in, it has a random number of nodes connections that it could connect to. Then they connect these edges one by one, and so every node comes in, it draws a copy from IID distribution of the random initial degree. Then you have an initial degree. Then with this initial degree, that's just basically the new node, the number of edges the new node comes with. Then you connect them one by one. So this is just the formal way of saying that. But it's just basically instead of one fixed edge for every new vertex, you have random number of edges to connect to, and you do this sequentially, one by one, connect one by one with the same preferential attachment rule. Yeah. And also, then here I present a stronger version of the central limit theorem that I just had several slides ago. So you can, for this model, so you can, even though every node comes with a random number of edges where you think the things might be messier, but it actually works out very nicely. It almost the same. The proof is in the same spirit with some technicality, but essentially it's the same proof. Yeah, and you can work this out that the maximum likelihood estimator is converges to a asymptotic normal law with Fisher information that only depends on the expectation of the random initial degree and the true parameter, which is nice. You can give confidence intervals. So this is simulation for the maximum likelihood. So for the for the truth of delta being 3, you can have you can have 1 million nodes, and then you get this sample mean of these estimations, and you get this, and this is sample variance, and which is very close to the predicted variance that is predicted by the asymptotic normal distribution. That's like 10% off, less than 10%, which is I think good enough. Also, yeah, this is a plot of the maximum likelihood estimator. So suppose you have you can have random initial degree, but the probabilities also work out this so-called fixed initial degree, where the random initial degree degenerates into a one-point measure, where every node comes with a fixed number of degrees. If you do this, then you have this simulation. Then it works out nicely for the MLE of delta. So yeah, so the truth is 0, and so this is so it's in a very small scope. So it's very nice. So okay, so as I mentioned that we have I'm going to talk about the sublinear case where you don't have this nice affine form, but only a sublinear form. So suppose you have a parametric family of the preferential attachment function, but also forget the random initial degree because that's too complicated in this case. So only every node comes in with one fixed edge to connect to, and so this degenerates into a simpler case. But the linearity of this preferential attachment function makes it very difficult to do it. But still, it's possible. So here you have a parametric family. You have a parameter, and you ask how to estimate the parameter, and then. You would ask why is it different from the affine case? Well, I can tell you because the proof becomes much more involved, in the sense that a lot of the things that is very simple in this case becomes random, and you really need to rely on the machinery from the branching process to prove all these convergences, and the proof is much more difficult. But nonetheless, you can still do it. I mean, you can prove that it is it converges to a asymptotic normal law and with a Fisher information matrix. Yeah. So the idea of the proof is again you write down the likelihood function and likelihood function. I write down the likelihood here exactly here because I'm going to use it later, where I propose some modification. So and then you apply the central martingale because this is a likelihood. If you evaluate the derivative of likelihood at the truth, then it becomes a martingale. Then you apply martingale central limit theorem on this likelihood. Then you have asymptotic normal law for the likelihood function. Then you sort of invert the likelihood to the parameter that you of interest. Then there's some work you involved, and there's the proof is technical, but still So what I'm going to propose the modification is that the remedy to a historical problem. So why is the reason? Because you see here this only depends on the final snapshot. So this is the proportion of vertices with a degree higher than k here at the time n. So this does not depend on history, but this, however, depends on the history. So you really need time from 2 to n plus 1. But suppose you only have a final snapshot of this network model, and how do you do it? And this is not feasible to construct the entire history. This is what we propose here. So what if we do not have a history? So first of all, you can show that this thing. So S is S. Oh, sorry, I'm forgot to explain the S. S is basically the sum of all total preferences on the network. So it's a summation of things. So you can prove because as I said, the empirical degree distribution converges to a limit. So this thing will converge to this thing, and then you have that replace H with the specific functions. So here it will converge to this one. Here it will converge to this one. So if you compare this and this is just the Cicero mean of these things. So this again will converge to this. But however, this thing also converges to this, and this only does not depend on the history. This only depends on the final snapshot at the time n. No history is required. So because here it depends on history, but it converges to this. And this does not depend on history. It also converges to this. So my remedy is that I replace this quantity with this quantity. Then you can solve the history problem. I remind you, this is work in progress. What I call the quasi maximum likelihood. So this is just we find the root of this quasi likelihood. This is not a likelihood anymore. You replace a quantity with another quantity, random quantity. So but the idea is that to prove the asymptotic normality, the idea is that you prove that they are not that different. So these two quantities, they're not that different with a certain rate. Then all the nice results still hold. Okay, so here I would have talked about the future outlooks. So what I'm thinking, what I'm trying to conceive is that what I call a stochastic blocker preferential attachment model. That basically means when every node comes in, it not only it has inherently some sort of labeling that comes from some certain distribution. Then the interaction, which vertex connect to, does not only depend on the degree, but also depend on the label interaction. So why is this good? Because first of all, it is so yes, this is just what I said. So first of all, it should, if you design this preferential attachment point, so how this probability is designed carefully, it should still give asymptotic power law. Also, it has the inherent community structure, which is very nice, can be very handy in modeling a lot of situations. And also, this is where you can probably apply non-parametric Bayesian stats. Yeah. Also, another way of working is that, as I said, you can work. Maybe we can work out the asymptotic normality of the empirical estimator that I conjecture, or that I'm pretty certain is normal. But this requires more study on the branching process. It might not be so easy. So so this is authors. This is me, and this is that person. So this is taken by Mrs. van der Waal. This is in Montreal, and also it has I need to thank Remco van der Hofstad and Rui Castro from Eindhoven. And also this is references. I think I finished early, but I think nobody would complain. So. So, do you have questions?
You've done the kind of a couple of scenarios for estimating your several models. What about the non-parametric assumptions on your F? Would you be able to deal with some non-parametric estimates of the underlying function?
Yeah, this is what the empirical estimator is about, right? Mm-hmm. The empirical estimator, what would This does not depend on any parametric form.
Oh, this one is completely non-parametric.
Yeah, it is. You only need to assume the monotonicity of the F, and then you can just apply for any fixed k, and for any fixed k it converges almost surely. I don't have the rate, but it converges asymptotically. So yeah, but it's more of a problem that of course you can do a lot of things. For example, if you can ask what is the rate, so you can maybe you can define a norm, but that's the question of another day.
With the line, and you said, okay, I cannot adjust, it doesn't work. It's very similar to you are in fact estimating the power law exponent.
Yes.
And so a method to do that is to look at a yield plot. You look at estimates over different sums, and you choose the value of k. You know about that or not?
You mean there is so yeah. So I think you are talking about this what is it called, the some sort of least square estimation of the power law exponent, right?
It might be least square.
Yeah. So what I think is that probably it is asymptotically equivalent. Okay. So at the end of the day, because if you work out everything, probably it's just the same at the end of the day.
If you had the simpler problem of just estimating the exponent of the power law distribution, could you do your MLE, or did I miss something?
I'm sorry, what? Say it again.
Apart from your problem that is not exactly estimating,
Yeah, I'm not estimating power law. This is just a byproduct.
So how come that you have a MLE estimator here? I did not understand.
Because
what is specific to your case?
I'm sorry, what? What is specific to my case?
Why do you have an MLE?
Oh, because the function we assume to be of this form, which is k plus delta. There is a parameter of delta, and the power law is 3 plus delta with the exponent 3 plus delta. So one way of doing this is that you estimate the power law exponent, then minus 3, right? The other way is we do it maximum likelihood, then we estimate the delta, right? So okay, so my bad, I didn't explain clearly. Sorry. Okay, yeah.
In the case where you had a random number of, when a node arrives, it arrives with a random number of edges. Mm-hmm. You said that the variance only ended up depending on the expectation of that distribution.
Yes.
But it seems like, I don't know, have you got any intuition for why it doesn't depend on the variance? Because if you could imagine that there'd be some degree distributions where I turn up with a whole lot of it.
This is I'm sorry, this is sorry, I'm sorry, I didn't mention it clearly. So it depends on the variance in a very wicked way, because if the variance basically, if you think of this distribution, is essentially is a probability distribution on the natural numbers, right? So it's the number of initial degree. So if this distribution follows a power law, and if this power law exponent is it depends on in a certain way. So if the variance is small, then at some point it will not matter. It will only depend on the another mechanism will kick in. So it doesn't matter anymore. But but we don't consider that case here. So we assume the variance exists.
You have a specific form for the not any distribution. It's some specific distribution.
I'm sorry, what?
So that was a psi distribution.
Mm-hmm. No. So I'm sorry. So the psi.
Yeah.
The psi here. So if the psi has some condition, like say I have finite cyclic moments, then it doesn't depend on variance anymore. So however, if you, of course we pose cyclic moment condition, but if you can do it with a weaker condition on C.
Are you sure it doesn't depend on the full degree?
Yeah, because so as if it is strong enough, then the asymptotic power law does not have nothing to do with the yeah. So yeah.
It depends on the asymptotic degree distribution, and then the distribution of the numbers also show up in that. If you have a low small tail, if you have big tails.
Well, I can show you the formula.
If there be small tails in the number of the edges that you add, then it doesn't show up. But if you have big tails, then
so if you so think like this. So this is the preferential attachment paradigm will give a power law, and if the random initial degree also gives, because it also has effects on the degree, right? Because it comes with degree. So if the influence of the random initial degree is so dominant, then the preferred attachment will not kick in, because suppose that you have too many. A general is always general large number of vertices, so the preferential actually doesn't matter anymore. So it's only the case where the degree does not depend on the initial degree so heavily that we consider, because otherwise there is no point in estimating the preferential attachment, right?
Okay. Yeah. Sure.
Mm-hmm. Okay. Pavel, do you need my laptop, Pavel?